Hi students, let's continue our discussion of electric field due to continuous charge distribution. In the last video we have discussed up to the infinite long wire and the finite long wire. Now the next object we are taking, the uniformly charged infinite plane sheet. So first of all I would like to tell you what is the infinite plane sheet means. Any plane sheet which is planar and whose dimensions are of infinite extent, means you can say the length as well as width both are of infinite extent. This also infinite, this length also infinite, and width is also infinite. Infinite means they are very large as compared to the distances involved. This thickness is negligible. Now this two-dimensional view of this sheet is shown here. So if we are seeing it from this side, then it looks like a plain paper type. So this is what it looks from this side. Now this thickness is negligible, and the point where we are going to find the electric field intensity, this distance is negligible actually as compared to the size of the sheet, means the extent of the sheet. This is the meaning of the word infinite. Infinite doesn't mean it is of infinite length. Even the 50 centimeter by 50 centimeter square plate can also be infinite if you are looking for electric field at a distance of 5 mm or 1 centimeter from it. So if this sheet is 50 by 50 centimeter and this distance is 1 centimeter, then you can consider this sheet as infinite. So I hope you have understood the meaning of the word infinite. Now, what is going to come? Electric field due to plain infinite charge sheet. What is the meaning of this? In the default case, plain infinite charge sheet means the charge is only on one face of the sheet. Like for example, if I say I have drawn this sheet, then there are two faces, one here, one here. If I take one paper, then on the paper one surface will be this, one surface will be this. Then charge is only on the one face, not on both the faces. This is the general convention. So if we have the charge only on the one face, charge is only on the right side face as shown in the figure, then the electric field intensity at any point near to the sheet is going to be, it is given by E is equal to sigma upon 2 epsilon naught. Electric field on right side of the sheet is also having sigma upon 2 epsilon naught. On the left side also has the sigma upon 2 epsilon naught. And not only this, electric field intensity at this point, 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 at all the points is going to be sigma upon 2 epsilon naught, and direction I hope you have understood. I have shown it. Now electric field intensity due to infinite plane sheet is sigma upon 2 epsilon naught. As already mentioned earlier, in default case we are saying the expression always for positive charge. But say for example, if this charge is negative charge, if instead of positive charge we consider the negative charge, let's draw the negative charge here. Say if this is negative charge, say this is, if this is negative charge, then the electric field intensity will be towards the sheet. like this. Due to positive charge away from the sheet, due to negative charge towards the sheet. This you have to remember, right? So electric field intensity due to infinite plane sheet of charge is sigma upon 2 epsilon naught, and it infinite plane sheet means charge is only on one face. It is not on both the faces. It is only on one face here. Now next we have the non-conducting infinite sheet. So this word conducting, non-conducting coming for the first time in the electrostatics here. So I would like to tell you the basic difference between the conductor and non-conductor with respect to the electrostatics context, right? Let's see this. We people are going to discuss this particular topic in detail after some time, but in short, only for this particular part and the next electric field expression due to the spheres, I would like to explain this. Let us consider we have one conductor. This is the conductor, left side. It is solid or hollow, anything you take. And right side we have the non-conductor. There also you can take anything. Now, what is the difference? If we give any charge to the conductor, charge Q given. Say for example, you try to place the charge here. Then what you say to attain the electrostatic equilibrium, in the electrostatic equilibrium condition, this charge won't remain here where you have placed. That will simply blast and it will come on the outer surface. Whatever charge you give to the conductor, that will come on its outer surface. And if the charge comes on the outer surface only, then whether you have given in the volume or you have given in the on the surface, in both the cases it will come only on the surface part. So here it comes. And second thing, this charge distribution means where the charge is more, where the charge is small. This particular fact depends upon the radius of curvature at that point. For an isolated conductor, please listen it carefully. For an isolated conductor means the conductor near to which no other conductor is present. The charge distribution is inversely proportional to the radius of the curvature. If radius of curvature is same at different points, then the charge distribution is going to be same at all the points. So if we give any charge to the conductor, that will come on its outer surface and the charge distribution of that will be in accordance with proportional to 1 upon radius of curvature, provided that is an isolated conductor. And we people are going to discuss most of the cases the isolated conductor only. Now see the second thing. Now if we give the same charge to the non-conductor, say we have given this conductor Q charge here, then here no automatic thing. Here the charge will be there only. Where we have placed, it will be there only. Very stable thing, right? Charge will be there only. If you say this total charge Q I don't give here, rather I will do Q by 2 I'll keep here and Q by 2 I'll keep here. Then Q by 2 will be here, Q by 2 will be here. It is not like conductor that entire charge will come on the outer surface. If you give this charge only on the surface, then charge will be there only. If you give the charge on the a part of the volume, then the charge will be there only. It means the charge distribution on the non-conductor can be in any way. It can be uniform, it can be non-uniform, it can be surface charge distribution, it can be volume charge distribution. Quite obvious for the hollow conductors, there won't be any case arising of volume charge distribution, right? So this is a very basic difference between the conductor and electrostatics, you remember. Now, here now, the next case, we are on the infinite sheet we are taking. We have non-conducting infinite sheet. Non-conducting infinite sheet means charge can be anywhere. We have the plane sheet having thickness tending to 0. So it means charge distribution is going to be only on the surface. So first case we are taking non-conducting infinite sheet having equal charge density on both the sides. On the right side as well as left side, the charge density is going to be equal. Now due to this we want to find the electric field. Now you see, principle of superposition we have used, and this one particular expression is there, electric field intensity due to charged infinite sheet. This itself is enough to write everything. Now let us say, now here two plane infinite sheets is there, one say right side and other left side, this one. Now due to this one, due to right side one, right, electric field intensity is sigma upon 2 epsilon naught, away from the charge because positive. And due to the left one, due to the left charge on the left side, it is also positive. So charge due to that sigma upon 2 epsilon naught, again away from the positive charge. So this is the positive charge. So field is away like this, right? Now total will come out to be, so this electric field comes out to be total sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, that is sigma upon epsilon naught. And on the left side if you see, due to the left charge, this charge, electric field will be sigma upon 2 epsilon naught. And due to the right charge again, sigma upon 2 epsilon naught. So if you add these two, you will get sigma upon epsilon naught. So electric field on the right side also due to both the surfaces, and left side also due to both the surfaces, and both are going to be in the same direction. That's why the electric field becomes sigma upon epsilon naught on left as well as right. If this charge distribution will be negative, if this charge density is negative, then the electric field will become opposite to our find direction, in this direction on the right side and this direction on the left side, right? It is clear. Remember, here we have considered the equal charge density on both the surfaces. Now consider the next case where the charge density is unequal, different on both the surfaces, but both are positive, sigma 1 also positive, sigma 2 also positive. Again here the concept of the principle of superposition will be used. Due to the charge on the right face, it will be sigma 1 upon 2 epsilon naught, and due to the charge on the left face, electric field at given point will be sigma 2 upon 2 epsilon naught. If you add these two terms, electric field due to the two surfaces, we will get sigma 1 plus sigma 2 upon 2 epsilon naught. And similar type of thing will come for the left side also. Due to the left face, sigma 2 upon 2 epsilon naught, and due to the right side face, sigma 1 upon 2 epsilon naught. Total comes out to be sigma 1 plus sigma 2 upon 2 epsilon naught. If you see, this is nothing but the previous case. This case, same charge density on both the surfaces, is a sub case or special case of this current situation. When sigma 1 equal to sigma 2, then we are going to have this also sigma upon epsilon naught. Now if we have the conducting sheet, now already we have told For the conducting sheet, charge will be only on the surfaces. So here, and that too inversely proportional to R. So here the charge density on both the sides on the conducting sheet will be equal. So electric field intensity directly I am writing here. It is sigma upon epsilon naught here and sigma upon epsilon naught here. If it is negative charge, then it will be towards the, if it will be negative charge, it will be towards the sheet. If it is positive charge, away from the sheet, negative charge towards the sheet. These 2 points are written, which are, again, we are going to see this in the behavior of conductors, but it might help you. One more thing you see, electric field intensity at any inside point of the sheet also we can find. Let's try this also. Any sheet you consider, conducting or non-conducting, doesn't matter to us. Charge density here given sigma 1 and here on the right side sigma 2. So already we have written electric field intensity on the right side comes sigma 1 plus sigma 2 upon 2 epsilon naught, and on the left side comes sigma 1 plus sigma 2 upon 2 epsilon naught, and in this particular thing it has been assumed that the electric field, the charges are positive. Now let's take one more case. Consider a point inside the sheet here. Now we want to find what is the electric field here. So left side, due to this one, electric field will be in this direction, equal to sigma 1 upon 2 epsilon naught. And at this point, electric field due to the right side charge will be in this direction, sigma 2 upon 2 epsilon naught. Again telling, I am considering both the charges positive. Very nice question can be framed by the people in the non-conducting sheet. On one side they give the positive charge, second side they give the negative charge. Questions can be framed, but here we are taking positive charge this side, positive charge this side. So at this particular point, which is inside the sheet, due to the left surface, field is towards right, and due to the right surface, field is towards left. Now considering whichever direction you are considering positive, I am considering rightward as positive. So I got the electric field, net electric field towards right as sigma 1 minus sigma 2 upon 2 epsilon naught. Now I hope you might have understood, if sigma 1 and sigma 2 are equal, then the net electric field intensity in the inside the sheet will be 0, right? Now let's take the next one. Same infinite sheet. Up till now we were taking the thin sheet. Now we are taking the thick sheet. Thick sheet means whose thickness is slightly more than, means not negligible. We are considering the thick, and here we are considering the volume charge distribution. As we are considering the volume charge distribution, it means it can be only non-conducting sheet. So we are considering the electric field intensity due to a infinite long non-conducting thick sheet having volume charge density rho, thickness T, and this is the central line, and from this central line we are interested in finding the electric field intensity at point P and Q. Point P is at a distance x from the central line, and point Q is also at a distance x. These two x are varying, means as a function of x we are finding the electric field intensity. At any inside point, the field will be given by rho x upon 2 epsilon naught. We can derive it very easily, but we are not going to be in that part. So electric field intensity at point P, inside point, is rho x upon 2 epsilon naught, and at outside point it is rho t upon 2 epsilon naught, while t is the total thickness of the sheet. So at any inside point rho x upon 2 epsilon naught, at any outside point rho t by 2 epsilon naught. I would like to mark the direction. Electric field direction will be this way. It will be away from the central line like this. Here if you say again like this, along the normal to the sheet and away from the sheet, and on the left side also away like this. But you remember, this is for positive charge. For negative charge, direction of arrows will be reversed. It will be towards the sheet. And if we draw the graph of this particular thing, it will come like this. Electric field versus x graph. X is the distance from the central line. So this type of graph will come, right? Now we have the next configuration as the spherical charge distribution. Now here also conductor non-conductor plays a very, very important role. So I would like to explain you that first thing. Now we have some conductor. See, so it can be hollow, it can be solid. So spheres is classified in two parts: hollow, solid. Hollow, solid. Now it can be also conducting or non-conducting. So four types of sphere we can have got: hollow conducting sphere, solid conducting sphere, hollow non-conducting, solid non-conducting. So four types of sphere: hollow conducting, solid conducting, hollow non-conducting, solid non-conducting. Now whether it is hollow conducting or solid conducting, if you give any charge, it will come only on the outer face. So for the hollow conducting sphere or solid conducting sphere, charge distribution will be only on the surface. Charge distribution will be only on surface. Now comes to the non-conductor. If we have the hollow non-conductor, hollow non-conductor. Now to hollow non-conductor, we can give the charge only on the surface. Hollow non-conductor, charge can be only on surface. But there is a difference. What is the difference? Let's see. Now in the conductor, charge density is proportional to 1 upon r, and for the sphere at every point radius of curvature is same. So for the conducting sphere, charge distribution will be uniform only. So whether it is hollow conducting sphere or solid conducting sphere, charge distribution will be uniform, right? If we give any charge to it. While for the non-conducting, to the non-conducting, we can give some charge and place it here only, or we can give some charge and place on this part only, and this part, left part, no charge we have given. Or we can give the charge to this part 1 coulomb, this part 2 coulomb, this part 3 coulomb. So in this way also we can give different charges to different identical segments. So charge distribution can be uniform or non-uniform. And on the solid non-conducting, if I take a solid non-conducting sphere, solid non-conducting sphere if I take, then we can give the charge throughout the volume also, or at any one particular region also, or on the surface also. But generally, in normal case, whenever we talk about the non-conducting solid sphere and we say it is charged, then it means we are considering the charge distribution is taking place along the volume, means throughout the volume the charge distribution has been taken place. So in short, now we can say there we are having the four types of charge configuration in spheres: conducting hollow sphere, conducting solid sphere, conducting non-conducting hollow, non-conducting solid. Among these four, the first three charge will be on the surface only. On the first two, charge will be always uniform. Third case can be uniform or non-uniform. So if I take these three types of same radius and same charge with an additional information that non-conducting hollow sphere charge is distributed uniformly, then it means these first three are same in terms of charge distribution and in terms of electric field. So when we say uniformly charged hollow sphere, when we say uniformly charged hollow sphere, then it can be hollow conducting sphere, it can be solid conducting sphere, it can be uniformly charged hollow non-conducting sphere, right? And when we are saying solid sphere, uniformly charged solid sphere, then it means only uniformly charged non-conducting solid sphere on which the charge is distributed throughout the volume, right? So now we are going to, you can have this, read this. Now we are coming to the hollow sphere. Hollow conducting sphere, solid conducting sphere, uniformly charged non-conducting hollow sphere. All will have the same surface charge distribution and hence the electric field intensity due to any of them is same. Due to all three, it will be same. And we are calling this particular thing as the hollow sphere, uniformly charged hollow sphere. So now we are writing the electric field intensity due to uniformly charged hollow sphere. So when we are finding the electric field intensity due to uniformly charged hollow sphere, consider a hollow sphere of radius r and charge q. Charge q is distributed uniformly on its surface, and we are interested in finding the electric field intensity at any point inside the sphere and outside the sphere. Inside point we have marked by S, outside point we have marked by P, and we are interested in writing the field intensity at S and P. Then for inside point, electric field will be 0. So here everywhere at every of the point, electric field will be 0. And here at any outside point, electric field will be given by Q upon 4 pi epsilon naught r square. So electric field intensity for at any outside point is similar like that of a point charge placed at the center. It means uniformly charged hollow sphere can be replaced by a equivalent point charge placed at the center for outside point. If you want to find the electric field at any outside point of the sphere, you forget about the sphere extended object, replace that by a point charge placed at the center, right? If we draw the graph for this, it comes like this. For the inside point, electric field is 0, and for the outside point, it is inverse square relation. Now, already in the, when we were discussing the sheet, I have told you electric field intensity is having the discontinuity at the surface charge distribution. Now here once again you can say electric field intensity here is having a discontinuity. At the surface, just inside is 0, just outside is non-zero. Now the next one we'll take electric field intensity due to uniformly charged solid sphere. Uniformly charged solid sphere means it is non-conducting solid sphere where the charge is distributed throughout the volume. Charge is distributed throughout the volume, and this is, we are considering the uniform charge distribution. Now here also we are interested in finding the field intensity at any inside and outside point. Inside point has been marked by S, outside point has been marked by P. So electric field intensity at inside point, here it is written the expression QR upon 4 pi epsilon naught R cube. QR upon 4 pi epsilon naught R cube, and in terms of the density also written rho R by 3 epsilon naught. And for outside point, electric field will have the same expression as like for the hollow sphere, Q upon 4 pi epsilon naught R square. For outside point, it is same as like of a point charge placed at the center or due to the hollow sphere. Now you remember this electric field is in radially outward direction like this way, right? Radially outward if positive. If negative charge, it will be radially inward. These type of points will be very helpful for you. So electric field intensity due to positive charge is radially outward, due to negative charge is radially inward. The graph for this will be like this. For inside point, it is linear function, and then at the surface it will have the value kq upon r square, and after that for outside point it is inverse square relation. That's all for now.